Section 9.3 is titled Applications in Probability. We're going to take a look at a couple of different applications in this section of how probability is used well, one of them at least is in gaming. The other one is more in terms of deciding whether a game is worth it to play. Okay? So here's our first one that we're going to take a look at, is something called odds. So let's actually talk about what it is, and then we'll talk about where you've heard it used before. Let P of A be the probability of the event A occurring, and P of A bar be the probability that it does not occur. Okay, so like the chance of rain, the chance it's not going to rain. You know, so if it's a 40% chance of rain, which we all sort of freak out about, really, that means you've got a 60% chance it's not going to rain. Okay, so that's what they're talking about here. If we talk about the odds in favor of event A, this is the probability of an event A divided by the probability of event A complement. So the probability that event happens compared to the probability that it doesn't. And the probability event doesn't happen, as we've seen before, is actually the same thing as 1 minus the probability of the event. All right, so 40 divided by 60, for example. If you want the odds against something happening, all you have to do is to flip the fraction upside down. Okay? So we have the probability it doesn't happen compared to the probability that it does. These are comparisons, right? That's what's really doing, is it's a comparison. How likely are you to win compared to lose? That's what it is. Now, we've seen comparisons like these before. Back when we very first, like probably first, maybe second day of class, looked at rational numbers, we talked about two ways to sort of talk about rational numbers. We talked about them comparing part to part and part to whole. Do you remember that? A part to whole comparison is the probability comparison, right? The percentage that you're going to get this to happen out of all possible scenarios. But an odds example is a part to part comparison, the likelihood that it will happen compared to the likelihood that it will not happen. Okay? So, where have you heard the word odds used? Everybody always gives that example. I'm so over it. Hunger Games. Where else? You've probably heard it used somewhere else too.
The game, what are the odds?
Yeah, you'll hear the phrase, what are the odds? You'll hear it used in regular English. You're like, well, what are the odds that that would happen, right? You've heard probably somebody say something like that before. There's actually a specific gaming industry that uses this particular one a lot. Does anybody know what it is? It is gambling, but it's a specific type. Usually you don't hear odds used there quite as much. You usually hear it used with horse racing. I don't know why specifically horse racing does it, but you'll hear horse racing doing it with odds a lot. So, odds. All right. Here we're going to do something that's not horse racing and not Hunger Games, just so you know. We're going to do it with marbles. All right, so we've got a set of 8 marbles, 5 red, 3 white, and we're going to choose one at random. So the first question is something we've done many times before now, okay? What is the probability that you'll choose a red? Somebody tell me, what's the probability you pick a red? 5 compared to 8. There are 5 red marbles, there are 8 marbles total. That's a probability, right? Comparison of the portion you care about to the whole thing. The next thing is, what are the odds that you will choose a red? That's 5 to 3, right? The number of reds compared to the number of non-reds. In this case, what did I have? Black, white, compared to the white. Okay? So we don't need to be concerned about this, but do be aware, odds don't have to be a number between 0 and 1, right? They don't, but probabilities still do. Could we also talk about the odds against choosing a red? We could. What would the odds against choosing a red here be? 3 to 5. Right? And you usually do hear it said that way with the word 2 between them. We've talked about that phrase before, right? 3 to 5, 2 to 5, those kinds of things. All right, so let's do the rain one. I mentioned this one earlier. I think these are the numbers I was using. If the probability of rain for the day is 60%, what are the odds against it raining? Okay, we want to be against it raining. So, all right, so we want, well, let me write it down. Where'd my thing go? Here. So we have, let's start first. What's the probability that it rains? That's 60% or 0.6, right? And what's the probability that it doesn't rain? I didn't hear anybody say it, but I know you know it. What is it? 0.4, right. So we want the odds against it raining. That's the same thing as saying the odds of no rain. Right, so we'd want the no rain chance on top and the rain chance on bottom. So this would be 0.4 over 0.6. We're not going to leave it like that, right? Decimals and fractions, we're not going to leave an answer in a form that's got both. So we could simply change this right now to 4 over 6, right? Multiply both by 10 over 10. And then what would we do? Reduce, so we get to 3. So it's a 2 to 3 odds. What did we say? Against it raining. Odds against it raining. All right, then there's a way to compare, of course, the odds in favor and the odds against and the probability and the odds and so forth. So if we have the odds in favor of event E as m to n, so m means the number of ways that it happens, n means the number of ways that we don't have our event happen, then the probability is m over m plus n, right? Our event happening compared to all possibilities. And then if we want the odds against it happening, the only thing that changes is the numerator is now n, because n is the ways that something doesn't happen. But it's still compared to the whole options, all possible options in the denominator. We did an example of this back when we were in chapter 6, where we had boys and girls in a classroom. We had the number of boys in the class, the number of girls in the class. We turned it into boys compared to the whole class. We turned it into boys compared to girls. I think I even gave a tested question that related those kinds of ideas together. We're just doing it now with this sort of new label, labeled odds. Okay? Okay. We are going to take a look at an example now. It's going to require a tree diagram. Yes, it is. We have a 3-child family. We want to create a tree diagram for it, okay? So, child number 1, what am I going to have to do? Yeah, there's only 2 options. It's boy or girl. So this is child number 1, boy, girl. And then I have 2 branches off of each of those because I have a second child. Options, boy or girl. And then I have 1 more set off of here. I think I have just barely enough room for my boys and girls. I need some numbers along my branches. What do I need? Yeah, either 0.5s or 1/2s, right? Because it's a 50-50 shot. I don't know why sometimes my point actually works really dark and sometimes it doesn't, but. Okay, so this first says we want the odds of having the same gender children. So looking at our tree diagram, I need you to find the places where it is all the same gender of children. Where is that? Top and the bottom. And along each of those branches, can I multiply the 0.5s together then? Certainly. So what would 0.5 times 0.5 times 0.5 be? 0.125, right. And that's both branches, right? So if we're wanting the odds of having the same gender, then we want the probability of the same gender compared to the probability that they're not the same gender. So what's the probability that they are the same gender? 0.25. How'd you get 0.25, Abby? You're right.
I don't know how I got
You're not sure how you got it, okay? Yeah. We found 2 branches over here, and we would add them together. So we would get 0.25. So that's our probability that we have the same gender children. So you shouldn't need to do a lot of adding to do the bottom right here. If the probability is 0.25 of having the same gender children, what's the probability that you have different genders of children? 0.75, right? It's the complement of that. And then we can change this into whole numbers. So this is 25 over 75. And how will that reduce? 1 over 3. So there's a 1 to 3 odds of having the same gender children. What are the odds against then having the same gender children?
It's just
Yeah, it's just that flipped. 3 to 1. Let me get the numbers in there right. 3 to 1. Okay, so don't go through all the work on the second one. There's no need for that, right? When we find the odds in favor, the odds against is just the reciprocal. Okay, so everybody have a pretty good feeling for how odds works. It's almost like we've really done this before. We've just given it a new label and applied it in a little different context. The next thing we haven't done before, though. Okay? The next one is called expected value. This is where you can make a decision about whether it's sort of in your best interest to play this game versus this game. You know, or whether it's in your best interest to play any game at all. If the possible outcomes of an experiment are A1, A2 up to AN, with the probabilities P1, P2 up to Pn, then the expected value is A1 times P1 plus A2 times P2 all the way down. Okay, so jot that down. And we will call a game fair when the expected value is 0. Now, in order to use expected value, we have to have outcomes that are numerical outcomes. So I can't actually talk about boys and girls or coin flips of heads and tails. I have to talk about something that has a numerical outcome, okay? Like a win or a loss of something. So when we're looking at these, we're going to always be looking at numerical values. Otherwise, it doesn't make sense to multiply things together. I can't multiply boy times 0.5, right? It doesn't make sense. So everything that we do with expected value is about numerical outcomes. So there is that sort of limitation in what we're looking at. But it really is applied to games, in which case it makes sense. So let me show you an example so you can see how it works. A really nice example is actually a roulette wheel. So you've probably seen some kind of a wheel before where you spin it and it has the numbers on it. A roulette wheel specifically has numbers from 00 up to 36. So how many slots are there actually on a roulette wheel? 38, right? So we have 1 to 36, and then we have a 0 and a double 0. There's 38 different slots. One way to bet on a roulette wheel is to bet on a single number. Okay, so you bet all your money on number 3, lucky 3, whatever. And then it's going to land on 7, and you're losing all your money. This is what's going to happen, so don't go betting on the roulette wheel, okay? But if the ball does land on your number, then you win 35 times what you bet plus the amount you paid. Okay, so everybody with me on the situation here. Okay, so it's a pretty big win, right? If you win a lot of money compared to what you bet. If you lose, they just take your money away. So the first thing we're going to do is we're going to talk about what is the probability that you will in fact land on 00. Probability. 1 out of 38. There is 1 00. There are 38 numbers. So 1 out of 38 probability. What's the probability that you will land on 0? Also 1 out of 38. Okay, so 1 out of 38 chance for each of those things to happen. So far, so good? And that would be true for any number. There's nothing special about 0 and double zeros, right? Any of those would be fine. All right, don't know why I have 2 of those in there. Okay, this is a for real scenario. This really happens. When my father-in-law passes a roulette wheel. Now, you have to understand, at a roulette wheel, they usually have a board next to it. It's electronic, and it will tell you what the last however many rolls have been, spins have been. It will say, like, it landed on a 3, and then it landed on a 12, and then it landed on a 15, and it landed on a 0, and then whatever. It tells you the recent history of the board. So if he passes by and he sees that in the recent history it hasn't landed on 0 or double 0, he'll bet on both numbers. Okay? So if he bets 1 chip on each number and the chip is worth $10, what is the expected value of his bet? Okay, so there's 2 possibilities here. Well, there's actually 3. One possibility is it lands on 0 and he wins. Second possibility, it lands on double 0 and he wins. And then the third possibility is he lands on anything else and he loses, right? So there's 3 different outcomes possible. So if you go back up here to the expected value stuff, the A1, A2, A3, whatever, we have 3 outcomes. Okay? You could say we have the outcome he wins, the outcome he loses, but since he could win in 2 different ways, we'll just keep them as their own little outcome. Okay? Sound good? Okay. So, one outcome that he wins, let's say it this way. Let me say it this way. Let's say amount that he wins. The amount that he wins compared to the probability of rolling the double 0 plus the amount that he wins compared to the probability of rolling a 0. We already know those 2 probabilities. We already calculated them. Plus the amount that he what? Loses. And it will be a negative number. That's how we will represent it. And then there's the probability of rolling the numbers 1 through 36. Okay, so is everybody clear on where everything's coming from?
Why does he do this? Does he actually do this?
He actually does this, yes.
Does he win often?
He's very lucky, and he will hit frequently. It's not statistically like a reasonable thing to do. We're about to find that out really quickly. But he's a lucky guy. Yeah. So, but mathematically speaking, you're about to show exactly why this doesn't make any sense. Okay, so let's see what happens. It says that he's bet 2 chips, right? So he's paid $20, right? Because the chips are each worth 20, or each worth 10, and he's paid 2 chips. And how much does he win if he wins? 35 chips. So let's just talk chips for a moment. He wins 35 chips plus the chip he played, right? So he wins 36 chips, but how many chips did he pay? 2. So what is his actual winning? 34. Is everybody with me? He only wins 34 chips. He gets 36, or he gets 35 back, but he paid 2. All right, so we're kind of thinking about this as like the net change in my wallet, what really happened. And each chip's worth $10, so if there's 34 chips, he wins $340. Okay, so the first possibility is that he wins, and he wins, $340. And we already calculated this on the previous slide. What's the probability of that happening? 1 out of 38, exactly. And it's the same amount no matter which way he wins it, right? If he wins it giving the 0 or the double 0, he still wins $340. And he has a 1 out of 38 chance either way. So depending on the game that you were doing, these wouldn't necessarily have to have the same winning values or the same winning probabilities. They could be different from one another. This game just happens to have equal values here. Now what happens if he loses? How much does he actually lose? He loses $20. Okay, so don't make yourself think somehow he loses nothing. He loses what he paid to play. He's $20 less in his wallet. And what is the probability that he loses? We didn't do this one yet. It is 36 out of 38. Right? Because he's paid on each of those 2 places where he could win, so there's 36 places where he can't win because he didn't put any money on those. Okay, is everybody good with the setup of the problem? Okay, now it's number crunching, and your calculator is your best friend, right? So grab your calculator out. Be really careful, don't round things too soon. My suggestion is to notice that these all have denominators of 38. Do you notice that? So what we really have here is 340 plus 340 plus, and I'm supposed to have negative 20 times 36. That's actually negative. What's 20 times 36? 720. So this is negative 720, and it's all over 38. Okay, so this keeps our calculator from rounding something funny or whatever. So what's 340 plus 340 minus 720? Negative 40. And go ahead and divide that now by 38. And we're talking money here, so we do want to round it to 2 decimal places. So is 0.5 correct? Okay. And this is money. So we got a dollar sign. So if he plays this game enough times, on average, he will lose $1.05 every time he plays. That's the statistical average. Should he play the game? No, it doesn't make statistical sense that he should, right? Kind of funny stuff. Okay, let's do another game. You guys have probably seen this one. Have you seen this one, Deal or No Deal? Or have you played it like Chuck E. Cheese or Dave & Buster's or something like that? My kids like this one a lot.
I play it like the whole time. It's so fun.
Yeah. Total luck, right? You guys get that, okay? So this is a lot like, the roulette wheel. There's really not any skill involved at all. You know that, right? Like, I'm going to pick number 3 because that's my favorite number, and this is when my brother was born, and that's when so-and-so, got divorced. I don't know, whatever the numbers are, they pick weird. Okay, it's crazy stuff. In the television show, Deal or No Deal, a contestant is down to 2 cases with equal probabilities of being chosen. The cases have $250,000 and $10. If you're the banker and you want to give a reasonable offer to the contestant, but not too lucrative, what deal would you offer and why? So, how can we use what we're talking about here to make this decision?
They want to be less than $250,000, of course, because
Mm-hmm.
you don't want to overpay or something.
Right?
If they have the $250,000 case.
So we want it somewhere in between the two, in fact, right?
Yeah.
Somewhere in between 10 and 250,000. We can use expected values to do this. Okay? So we don't have the same kind of scenario exactly on the last one. Like, you're not really losing anything, right? You win either way. It's just one win is a big win and the other win is like, yay, I can go to McDonald's, or something like that. Okay, so our expected value here, one option is that we win 10 bucks. How likely is that to happen? 1/2 or 50%, right? Times 1/2. So we have the outcome times the probability. The other outcome, we're very excited, and except for the fact that we have to give half of it to the government. We don't like that too much. But we can do a lot of good with $125,000. I know I could. I'm sure you could as well. You could probably pay your student loans, right? That would be nice, wouldn't it? That'd be awesome. What's the likelihood you win the $250,000? 1/2. Okay, so let's go ahead and calculate this. And could we do this with 3 cases? Yeah. We would just have a third option on here, and all the probabilities would be 1/3. So is there anything special about this sort of description with 2 cases? No, we could do it for 4 cases or 10 cases or whatever, and we could do the same thing. All right, so what does this give you if you multiply these together and add them up and so forth? What do you get? And remember, it's a dollar amount. This is money we're talking about. Okay, so the number we actually come up with is $125,005. Now, I don't know about you, but the banker I don't think has ever offered a weird number like that before. It's a little odd, right? But the principle is still there. What would he be offering? Around $125,000, right? That would be the reasonable kind of offer. So you'd offer approximately $125,000. Slightly more would mean that the contestant might be more likely to pick it. Slightly less might mean they're less likely to pick it. But this would be the ballpark that we would be expecting the offer to be around. A ballpark that as the banker we would be expecting to pay. Does that make sense? Okay, so it's an expected value. All right, this is the last one. Because what topic would be complete without a lottery? Lottery, lottery. In a given lottery, we know that the odds of winning the lottery are 55 million to 1. So let's start with probability. What is the probability then that you're going to win the lottery? Is it? 1 over what?
5 million and 1.
Oh, okay. 55 million. I know it feels funny to say it like that, but it's actually 55 million and 1. All right, so those of you who finally caught the and 1, explain. Someone. Okay, the description started out with the phrase odds, right? So odds against winning the lottery, or odds of winning the lottery. 55 million people lose. 1 wins. That's the odds that we're given, right? So you have to be careful with the fact that that's denominator. I know it doesn't make a lot of difference when we actually calculate the percentage here, but it actually should be 55 million 1 on bottom. This is the probability of winning the lottery. Okay, is everybody good with that so far?
It's like part over the whole.
Right, exactly. Part over whole. Okay, good. Now it says if the grand prize is 14 million and a ticket costs $5, is the game fair? So let's pause. Fair doesn't mean I like the game or I don't. That's not what it means. This is not fair, right? You guys have never said that to your parent, have you? Of course not. And I never hear that in my house either. So fair here had a mathematical meaning. What did it mean?
It was equal to 0.
Ah, what was equal to 0, Hannah? Did you remember?
You'd be able to get your answer back to 0.
Okay, and what answer is she referring to? You guys remember?
The expected value.
The expected value. So this question is asking us, is the expected value 0? Everybody good with that? Well, in order to answer that question, we're going to actually have to find the expected value, right? Okay, expected value then. Our expected value, well, there's really only 2 outcomes here, right? We win or we lose. Okay, so we need the probability, or I'm sorry, we need the value that we get if we win. So if we win, what do we get? $14 million. Make sure you write that in millions so that we can calculate this appropriately. So there's 14 million. How likely are you to win? Yeah, that's part A. The 1 out of the 55 million, 1. Plus. Okay. Now we need to go back and check on something really quick. It told us something that we overlooked. It told us that it cost us to play the game $5. So we pay $5 to play, we win 14 million. Did we really win 14 million? Not exactly. We actually won what? We got lots of 9s in it, don't we? Okay, so let's cut this out and let's change that. So this number really should be 13,999,995. That's actually our winnings. All right, then we've got the value of losing. So what's the value of losing? -5. And what's the probability of losing? Okay, so I'm most concerned with the setup. Does everybody understand the setup of the problem?
Why is it 13,999,995?
Okay, So the reason is because if we paid $5 to play, Hannah,
Okay.
then we have to take that $5 away from our winnings.
Okay.
We didn't really, our net change in our bank account, so to speak, or our wallet actually didn't count that $5.
Okay.
So we take that 5 off. Okay then. Somebody grab a calculator for me. What do you have?
I don't
Yes.
understand why it's the -5 times that over that.
It's always the change in our wallet. The value is the change in our wallet if we win versus if we lose. If we win, our increase in our bank account is 13 million and some change.
55 million over 55 million.
You mean the probability next to it. Okay, so the probabilities come from this one up here, right here. If you've got 1 out of 55 million won that win, how many lose? The other people, right? There's 55 million won people who played the game. 1 wins, so 55 million lose.
Okay.
Yeah. Okay, any other questions on setup? Okay, what's your calculator give you for this?
Well, isn't it all over the same number?
It is. So you could actually just take the numerator, 13,999,995, plus the -5 times 55 million.
-4.7.
4.74.
Yeah.
Okay, so this is the expected value. Is the game fair? No. Why not?
You're expected to lose about $5 on top.
Yeah, every time you play, on average, you're going to lose $4.74, right? That's an average amount, okay? So the game's not fair, no, and the reason is because the expected value is not 0, right? So the game is not fair. Okay, so here's where the catch comes and you start thinking, now wait a minute here. As with many state lotteries, the proceeds are often said to benefit education. Have you heard that before? Yes? Okay. That's how casinos were finally allowed in Ohio when we were there, is that they were said to benefit education. That was the benefit. Under these conditions, if all proceeds benefit education and 1 million tickets are sold, what is the expected value from the lottery sales? Okay. So if we as customers are expected to lose $4.74 on average, then that means that somebody else is keeping that $4.74 on average, right? The lottery commission or the state or the education or whoever. So this $4.75 is a negative to us, but it's a positive to whoever's keeping it. So everybody good with that? Okay? So that's the value that this is talking about on part C. It's the $4.74. On average, they make $4.74 on every ticket. So if they sell 1 million tickets, what would I need to do to figure out how much money they make? Multiply this by 1 million, right? So what would their earnings for education be? Okay, so roughly speaking, 4,740,000. Okay? That's the expected outcome. That's not really what happens though, right? And I don't even mean in terms of the education. Really, either everybody loses or somebody wins. Those are actually the two outcomes, right? There's not a perfect scenario, average case thing that we just did. That's sort of a mathematical process by which we can decide whether to play the game or not, but that doesn't really tell us what happens. So what are the actual possibilities? Well, one possibility is that someone wins. Let's say no one wins actually first. That's an easier one to do. No one wins. So if no one wins, how much money does the commission make?
Well, not much. Right?
They sell 1 million tickets, right? Nobody wins. So what do I need to multiply my million by? It's not the 475 or 474. 5.
That's how much tickets cost.
The tickets cost $5. You with me? Tickets cost $5. They sell 1 million tickets. Tickets cost $5. Nobody wins. They keep all the proceeds. Make sense? Okay. So this is $5 million. That's one outcome. The other outcome is that someone does win. Now let's think about it. If someone wins, they still brought in $5 million of income, correct? But what happens when the person wins?
You take away however much it was for 55.
Yeah, how much was it that they win?
14.
So what do you get if you have 5 million and you take away 14 million? Negative $9 million for education, right?
Where'd you get the 14 million?
It was in the problem to start with.
Oh, okay.
Yeah. So here's the problem. You're either rooting for everybody to lose money so that the education wins, right? Or you're rooting for the person to win, in which case the education has absolutely no benefit to this at all. Do you guys see the problem with that? Well, that doesn't make any sense. But this is how this happens all the time. Crazy, right? Crazy stuff.